Okay, so today we're doing this really cool log thing. It's not it's not as weird as it looks, but it's kind of weird. Logs have this really interesting and unusual property. It's an algebraic property, and it needs to get learnt because you totally use this in Math 100. If you don't know how to do this properly, a ton of the curriculum's not going to make sense after about a third of the course. So logs have this really bonkers property when it comes to turning multiplication into addition, turning exponents into multiplication, turning division into subtraction. And the result is, if you understand these properties of logs, you can dramatically simplify the calculation you're doing. At the end of this, you're going to understand how to split logs up where their input is two things multiplied together. You're going to understand how to split that into two logs that are added together. You're going to understand how to, that's that one. You're going to understand how to take two logs where the input is divided, one thing divided by another, and write it as two logs subtracting each other. You're going to understand the exponent rule, which involves bringing powers down out front, exponents down out front of the log. I'll explain when we get there. You're going to understand how to interpret reciprocals as negative coefficients. And then you're going to be able to use these four properties to evaluate some given logs by hand. You can only do it with special ones. So in this case, I'll be giving you special ones to do where you can evaluate them by hand without having to, look them up on a calculator. So essentially, the logarithm property is this. It can turn multiplication of input into addition. And it can turn division into subtraction. This is a bonkers property. Really only logs have it, and the fact that logs have it make some more advanced calculations that you'll see in your academic career super easy. All right, without further ado, it looks like this. Log, you know what? Yeah, we'll go with the log base 10. 4 times log of 8. You can rewrite this expression as the logarithm of 4 plus the logarithm of 8. Let's try this before we go any further. This is equal to, of course, the log of 32, right? 4 times 8. I can evaluate that using my calculator right now. Log of 32. It's equal to 1.50514. Fine, okay? I can also evaluate each of these. So log of 4 is equal to 0.602059, and log of 8, oh, wake up, log of 8 is equal to 0.903089, and you add them together, 0.602059, and you get 1.50514, right? They're the same number. It's true, you can. And the same thing goes with subtraction, or division rather. If you divide two numbers, that's equivalent to subtracting them. So let's try that right now. Let's see, 4 divided by 8 is 0.5, right? Plug that into my calculator. Log of 0.5 is equal to minus 0.301029. Right. Okay. So now I'll evaluate each of these two. The log of 4, that's equal to 0.602059. And the log of 8 is equal to 0.903089. Right? And now I subtract them. 0.602059 minus answer minus 0.301029. They are the same. This property of logs is super useful a little bit later down the road. I want you to try this one, the following one yourself. According to my rule, ln of 5 times 3 divided by 7. Okay, hold on. 5 times 3 divided by 7. In other words, we're calculating ln 2.142857. According to this rule, you can write this expression out as ln of the 5 plus ln of the 3 minus ln of the 7. Evaluate each of these on your calculator now and compare. Ln of the 5, that's equal to 1.6094379 plus ln of the 3, that's 1.0986122, and ln of the 7, that's equal to 1 minus 4591014. Alright, now we add them up. 1.60979 plus 1.0986122 minus answer. 0.762139. Alright, now let's try the ln of that other number. 2142857. 0.762139. Yeah, they're the same. Okay, so it's not a coincidence they're the same. This particular rule comes from somewhere. I'll just write down the rule here. So A times B divided by C can be written as log of A plus log A of B minus log, you know what, I'll put a D in there too, A of D minus log A C. Okay. These things, I mean, multiplication and division are all kind of related, right? So if things are multiplied, you can break them up into pieces. Each one of them gets its own log term. The ones in the numerator get pluses in front of them. The ones in the denominator get minuses in front of them. Okay? So this is a super handy rule. Where does it come from? That's a good question. Don't worry about it right now. It comes from, we'll talk about where it comes from. It's a fundamental property of logs, and the reason why has to do with where logs come from, what purpose they fill in the big ecosystem of functions. They do this for a reason. This is one of the characteristic properties of logarithms. So don't worry too much about where they come from. Instead, let's use this in a different way. It may be a little bit more useful way. Consider the following. Log base 3 of 4 plus log base 3 of 6 minus log base 3 of 8. I don't know how to evaluate each of these. Suppose I lost my calculator in a car accident. Oh no, it's so sad. I lost my calculator. I can't evaluate logs, but I can still combine them together. Because look, each of these has the same base. When you split up a dog like this, each of them has the same base, and so it follows that if you add or subtract logs with the same base, you can add or subtract. You can combine them together to make one big log. So in this case, what you're going to do is, for all the ones with positive coefficients, or pluses, they're going in the numerator, and the minus ones are going in the denominator. 4 times 6 divided by 8. And that's a number I can evaluate. Even if I don't have a scientific calculator on me, I can still evaluate it. It's 24 over 8. Log 3 of 3. Oh, I know what log 3 of 3 is. It's equal to 1. Right? So this trick, breaking it up or combining them into 1, is actually pretty helpful for being able to calculate things. I want you to note before we go on, I'm going to give you some examples, but before we go on, quick warning. You're not allowed to combine these two together because their bases are different. So these two have to stay apart. That said, if the bases all match, you can combine them together. Okay, so let's try one here. Try this one yourself. And then after that, try this one. And then after that, try this one. And heck, while you're at it, how about one more for the road, huh? Log of 12 of 7 minus log 12 of 49 plus log of 12 of 14 minus log 12 2. All of these are ones that I chose them specially just as a form of doing practice. But all of these are logarithms that we can evaluate even without a graphing or a fancy calculator or any type of calculator. So I combine them together. Log 2. 9 divided by 6 times 3 over 2. So it becomes log base 2 of 9 divided by... Alright, 6 times 3 is 24. No, 6 times 3 is 18 divided by 2 is 9. So this is log base 2 of 1. What's that output? That's 0. We learned that in the last video. Alright, let's try this one. Log base 6, 12 divided by 2. So 12 divided by 2 is 6. Oh, I know that one. That's 1. Log base 24, 3 times 2 times 4. Alright, so that's 624. Oh, hey, look. 24, so that's equal to 1. Yeah. And this one is log 12, 7 divided by 49 times 14 divided by 2. Weird. Alright, so that's 7, 8, 91? And 91 divided by 90. Oh, 91. Okay, so log 12 of 1, that's 0. At this stage in the game, the answer is always 0 or 1. But you still have to figure out which one it is. Okay. So. This particular attribute is a pretty useful aspect of logs, but this isn't the end of it. Logs have a different algebraic property. And it goes like this. So let's consider this expression. 3 to the 5. Okay? Cool. It's an exponent. Exponents are fun. We can write this on out. This is 3 times 3 times 3 times 3 times 3, right? 5 of them. And using that property of logs, this is 3 plus log 4 of 3 plus log base 4 of 3 plus log base 4 of 3 plus log base 4 of 3. Here's the fun part. Each of these is exactly the same. The reason each of these is exactly the same is because each of these numbers is exactly the same. The reason each of these numbers is exactly the same is because it's 5 to the 3 to the 5, right? So automatically, when it's some term to some power, you're going to get the same logarithm over and over. Why is that useful? Well, think about it. How many terms are there here? There's many terms in this list as there are terms in this list, and there are as many terms in this list as there are 5. Right? So, in other words, when you have a base, when you have a logarithm of an exponent expression, you're going to end up with a bunch of log terms in terms of the base of the exponent, and the number of terms here is going to be whatever that number is. It's over and over added together, so the answer is 5 times log 4 of 3. This is the second property of logs. It goes like this. If you take the log of some number b to some other power n, you can rewrite this expression as you bring the n out front, n times log a of just the number. Okay? So let's test this before we go any further. Ln 2 to the 7. Okay. 2 to the 7 is equal to 128. If I take ln of 128, you get 4.85203.026, whatever, okay? According to this rule, I can take our original expression and bring the 7 out front. 7 times ln of 2. So ln of 2, what is ln of 2? 7 times 0.693144718. 4.85203.0264. It's the same. Try it yourself. Okay. Now, like try your. Well, okay. Here, I'll give you one to try. I mean, don't just sit there. Try this one. Log base 10 of 7 to the 6. So that's equal to log base 10 of 7 to the power 6. That's 117649. So that's 5.07058 ... Apparently, this is equal to log 7. Right, so that's 6 times 0.845098, which is equal to 5.07058. Oh, it's the same number. Okay. So you'll see that it's true. Hooray! That's very interesting, and it works for any number you choose. But there is a bonkers consequence to this. I want you to think about log base 10. Just for example, what's log of base 10 of 10? Eh? What is it? It is equal to 1, because the input is the same as the base. Cool. What's log base 10 of 100? Well, 100 can be written as 10 to the power 2. So you can bring the 2 out front, and that evaluates as 2. Log base 10 of 1,000. So 1,000 can be written as 10 to the 3, which becomes 3 times log 10 of 10, which is 3 times 1, which is 3. Yeah? This shows actually one of the fundamental properties of logs. We haven't really talked about log behavior yet, but this is a big one. when we input larger and larger numbers into the logarithm, what it does is spit out numbers that aren't increasing very much. I mentioned when we in the very first video that logs kind of, the idea behind log is that, you know, it takes a multiple amount for the input to increase, for a multiple amount of change in the input to make the output increase by 1. That's essentially what we're talking about. The input has to go up by a factor of 10 for the output to increase by 1. More on that eventually. Okay, so for instance, log base 10 of 1 over 100. What about that? Well, this can be written as 10 to the minus 2 and it's just minus 2. Okay. It's pretty cool. You can evaluate these particular numbers using logarithms or by hand. I'm going to show you some specific examples where we're going to be doing things by hand, but I want to review what we've just talked about. Know these rules by heart. The first one is the exponent rule. You bring the exponent out front, and then you take the logarithm of the bare number. And the second rule, b times c over d. Okay? You can rewrite this as log of a of b plus log of a of c minus log of a of d. Don't forget the minus sign. Okay. If we combine these principles with, that's not the pen I'm supposed to be using, the ones we talked about last time, log of a, if we take the logarithm of the base, you get 1, and you take the logarithm of 1, and you get 0. Oh, hey, by the way, where does this come from? I mean, we showed that it was true, and we showed that it was true for all. We showed that it was true for all logs according to the change of base formula. But why is this true at all? Like, why is it true with ln? Why is ln of 1 equal to 0? What do you think about it? Ln of 1. Okay, well, instead of ln, let's do 10. It's easier to understand. Log base 10 of 0. Why is that equal to bleh? I got it backwards. Log of 1 equals to 0. Okay, so we argued that all of the other logs were 0 because of the change of base formula. So this one's 0, so they're all 0. Why is this one 0? If you think about it, log 1, you can write 1 as 10 to the power 0, right? And you can bring the 0 out front. And so it's 0 times 1, which is equal to 0. Yeah? All right. So the idea is, in the following set of exercises, we're going to be using these for pieces of information to evaluate logs by hand. That's like, I don't know, building a log cabin by hand. It's equally impressive. Before we go on, one thing I'm going to need you to be able to do here is do some prime factoring. Specifically, I need you to be able to recognize things like 9 is equal to 3 squared, or 25 is equal to 5 squared, or 16 is equal to 2 to the power 4, that kind of stuff. I'll probably give these to you if we're doing like a test or something like that, but it's a simple procedure to be able to do. I don't think it's demanding too much. So there's going to be that aspect to it. I'm not a real bonkers, like, I only know, let's see, I know 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared off the top of my head. 11 squared, I kind of know. 12 squared, I barely know. Yeah. And then when it comes to cubes, I know 1 cube, 2 cube, 3 cube. I don't think I can recognize 4 cube. And then for to the power 5, I know 2 to the power 4, and I know 2 to the power 5. There's not really all that many prime factoring things I'm going to ask you to do. But the following explanation kind of relies on you being able to do a little bit of simple prime factoring in your head. Okay, so how can I evaluate this by hand? I promised that I could. What I'm going to do is I'm going to combine them all. They all have the same base, right? Base, base, base. And I'm going to combine them all into 1. 6 divided by 9 times 12. And you're going to multiply that out. You can use a calculator to do the multiplying if you want. That's equal to, no, it's not equal to 9. It's equal to 72 over 9. So it's equal to log base 2 of 8. And then 8, like I said before, 8 is just 2 to the power 3. So you can write this expression 3 times log 2 of 2. So that's equal to 3 times 1 is equal to 3. Okay? That's one way to do it. It's not the only way to do it. If you can do prime factoring, I mean, this way works, and it works pretty good. But if you can do prime factoring in your head, or at least kind of readily, so I don't just mean like figure out which ones are squares. I mean like if you can go like, hey, 24 is equal to 4 times 6 times 4, so it's equal to 2 times 3 times 2 times 2, so it's equal to 2 to the power 3 times 3 to the power 1. If you can do that, then you can do a ton of logs in your head. So let me show you an example of this. Instead of combining them all and then multiplying them, if you can do prime factoring, you can break them up into smaller pieces and then combine the smaller pieces. Most of them will cancel out. It's pretty fun. Watch this. Oh, that's not right. Log base 3 of 6 plus log base 3 of 12 minus log base 3 of 8. I don't know what any of these are. I could plug them into my calculator, I guess. And if you want a calculator, this one, to see what the answer is, be my guest. But I want you to also be able to do it this way, at least a little bit, for simple ones. This one becomes log base 3 of 2 times 3. This one becomes log base 3 of 2 times 2 times 3. And the last one becomes log base 3 of 2 times 2 times 2. Okay? So when you expand them out, the first one becomes log base 3 of 2 plus log base 3 of 3 plus log base 3 of 2 plus log base 3 of 2 plus log, I wrote a 3, log base 3 of 3 minus, alright, now I need to break these guys up, log base 3 of 2 plus log base 3 of 2 plus log base 3 of 2. And like I said, if you would rather do this question by combining them all and multiplying and dividing them and then factoring, that works too. And then we do cancellation. So this one cancels with this one, and this one cancels with this one. This one cancels with this one. So after you cancel, you get log base 3 of 3 plus log base 3 of 3. And so that's equal to 1 plus 1, which is 2. Yeah? That's fun, right? All right. How about one more example to try? Like I said, it doesn't matter how you do these, but you can do these in your head, or at least with a simple calculator, without having to evaluate the log. Let's combine them all together. So this is 8 times 6 divided by 9 times 12. times 6 times 12 divided by 9, that's 64. And 64 is equal to 4 to the power of 3. Yeah. So this is equal to 3 log 4 of 4. So that's equal to 3 times 1. It's 3. Hooray! All right. So what do I need you to be able to do? These properties of logs are pretty important algebraically a little bit later on, so it's important that you know how to do them. They're not that useful right now, but we'll see some examples in the near future. But for the time being, let's consider our old friend the medicine wheels. Bring it over here, buddy. Okay. First thing is that if your log has two things multiplied inside of it together, you can rewrite this as log of the first thing plus the log of the second thing. This works both ways. If you have these ones, you can rewrite it like that. Right? Related to this is the division formula. If you have things that are dividing each other, you can rewrite this as subtraction. These two are mirror of each other. They work together. Next, there's the exponent rule, which says if you have something to an exponent, you can bring the exponent out front. And that helps you evaluate things. And the last one, I mean, it makes sense. It's just an application of the exponent rule. And it's also, you know, comes from this deal. Like if m is equal to 1, oh heck, let's just prove it right now. So this is equal to minus log a of b. I can explain where that comes from in two ways, but essentially it's consistent with this thing. So the first way to explain it is you can write our reciprocal as b to the minus 1 and then bring the minus 1 out front. The second way to explain it is in terms of this subtraction division rule. So according to this, if you expand it using this formula, you get, okay, so you get log of a of 1 minus log a of b. And as you know, log a of 1 is 0. So you get minus log of b. The result is that we end up with a really effective kind of means of doing calculations. Just like in exponentials, where we saw that multiplication became addition, division became subtraction, powers became multiplication, like two exponent to another power, you multiply their exponents together. Same thing here. Multiplication becomes addition. Division becomes subtraction. Power turns to multiplication. Yeah. This is an important theme, and it's not coincidental. We're going to talk more about the relationship in the near future, but for now, that's it. Have a good day.